ocean basins. Is that basically correct? Okay, the features of the continent, which are the shales and the young mountains, the old mountains, and the stable platform. And that probably was close to the end. Okay, so today we're going to start with, for science, a relatively new idea. And this is continental drift. It's a new idea as far as being accepted by the scientific community. The idea of the continents being together goes back about 300 years, but the data was not available to prove that this was a viable theory. And it didn't happen until literally the beginning of this century that the idea was initially put together by a German meteorologist, not a geologist, but a meteorologist. And the German meteorologist was Alfred Wegener, not Wegener, but Wegener. And Wegener said basically in his book, which was published in the second decade of the 20th century, The Origin of the Ocean Basins and Continents, that's the book, The Origin of the Ocean Basins and Continents. Wegener proposed that all of the land masses at one time were fused together in a supercontinent called Pangaea. The supercontinent had all of the major landforms tied together, and he suggested that sometime during the Paleozoic, and as data would indicate, during the last stages of the Paleozoic, about 30 million years ago, we had this supercontinent. All of the land masses, from Greenland down to the Antarctica, were joined together. Now this then does not include the small islands that we see, such as Iceland, Hawaii, and many of the islands of Indonesia. But the major land masses, the land masses that had continental shields on them. When we mentioned last time that the shield is the core of every continent. So if it has a shield area, it was attached into this one supercontinent. Well, when Wegener proposed his ideas, the scientific community said, yeah, what does he know? He's not a geologist. All he's doing is writing trash for the masses. And there is America's most famous geologist at the time, was a man by the name of Chamberlain. And he spent much of his time at Harvard, Yale, and the University of Wisconsin. And Chamberlain said basically, garbage, it's a fairy tale, and it's, again, food for the masses who can't think. So he literally gave it no support whatsoever. And he argued that Wegener had not included in his ideas any method that these supercontinents could move apart, that these continents and masses could move. He just proposed they were together, and he gave some reasoning why he thought they were there. And what we're going to do this morning, or this afternoon, pardon me, is look at some of the ideas that Wegener proposed as proof for the theory of continental drift. Now, he proposed this in a book in the second decade of the 20th century. Give away my age a little bit. When I took my first geology course in the early 60s, we're still fighting the dinosaurs. In the early 60s, at the end of the semester, my geology prof said, here's an interesting theory. It hadn't been accepted yet in the academic community, and it was not accepted until the late 60s. So literally, it's a theory that is new by whatever standards you may want to use. And before we get to his ideas. So just a couple of transference overhead I want to look at. Okay, what Wegener proposed, let me turn on some lights. Better? And your book covers this to a limited degree. What Wegener proposed was the outer part of planet Earth was composed of large unitable plates. These plates are composed of ocean basin material and continental material. So they're part of the crust in the upper mantle. So the upper mantle and the crust area composed of what Wegener and what other scientists have considered 7 major plates. A host of minor plates, and then a couple dozen insignificant small plates. So we have these units out on the outer edges of planet Earth. And what Wegener proposed was these plates that move independently of one another. They float on the asthenosphere. Remember, the asthenosphere was that solid that showed flow characteristics, and he proposed that these plates floating on the asthenosphere move about. Now, this first diagram up here, or map, basically outlines the plates. We look at this, literally, the mid-oceanic ridge, which runs through this area, the oceanic ridge that runs through that area, is a dividing line between plates. So you have one plate on this side called basically the North Atlantic plate, North American and North Atlantic plate. And over on this side, you have a massive plate that extends from here all the way over, and that's the Eurasian plate. Europe and Asia are part of that. South Atlantic plate, and over here we have the Pacific plate and so on. So what we have here, first of all, are the ridges of the ocean basin. And the ridges are a dividing line between the plates. At the very top of the ridge is a zone called the rift, R-I-F-T zone. And it's at the rift zone that these plates pull apart. It's at the rift zone that we have new volcanic materials forming. And they are mafic in characteristic. Mafic, they're dark in color, they're high in iron, they're high in magnesium. They're very, Hawaiian Islands, if you've ever been there, that's a typical mafic rock unit. So at the mid-oceanic ridge, we have volcanic materials rising to the surface. As they rise to the surface, they move away from that centralized point. So from the rift zone, and what happens is literally at the center of the mid-oceanic ridge, there's something like this. This part of the ridge is moving in that direction, this part is moving in that direction, and this is the rift in the center. It's tearing it apart. Now, we have rift areas on land as well. A primary rift formed the Red Sea in this area. This part of Africa, which is now Saudi Arabia, was once attached to Africa, and it has just ripped apart, separated apart. This part of Africa, which is the Horn of Africa, also has a major rift zone that runs right through these lakes, and this part of Africa will become separated from the main mass in time. So the continental drift has been going on for 225 million years. It continues to this day, and we'll look at that in a little bit. The trench zones is where these plates come together. So the plates are coming together at the trench zone. So we have plate A and plate B coming together, moving in this direction. And so at the trench zone, also known as, what we'll call a trench, subduction. Okay, so it's a trench zone, it's a subduction zone, The plates are coming together.